You synthesized your compound, you've purified and isolated, and now it's time to determine the identity of that compound. So let's talk about 3 ways to characterize a compound: IR, NMR, and MS. Let's say you're given a colorless liquid and told it's either ethanol or rubbing alcohol. What method would you use to identify this liquid? So stop the video, think about this for just a second. So here are some properties of each compound. Note that the density of ethanol and isopropyl are the same. The bond types are the same, but the boiling points are different, so boiling point is the weight. Here's another example. C4H10 has 2 isomers. Which method would you use to identify which isomer you have? So stop the video and think about this for just a minute. Here are some properties of these substances. Based on properties, it looks like boiling point is the way to identify that substance. Let's focus on 3 ways to determine the structure of a compound. We'll look at IR to determine the bond types, NMR for the carbon skeleton, and mass spectrometry to determine the molecular weight. Here's a picture of the mass spectrometer. So a sample is injected and vaporized in the spectrometer. An electron smashes in the sample, forms a molecular ion and other fragments. Those ions are deflected by a magnet where it goes down and is detected by a detector. So it's sorted by the mass to charge ratio. We will look at a mass spectrum to determine the molecular weight of a compound. That will usually be the biggest peak in the mass spectrum. So pentane, which has the formula C5H12 and a molecular weight of 72, shows this peak here. Here's toluene, so stop the video and determine the molecular ion peak. Note that toluene has a molecular mass of 92, so this peak here is the molecular ion peak. Note that the smaller peak represents an isotope of carbon, which will give a mass to charge ratio of 93. So a mass spectrum gives us information about the molecular weight of a compound, which can tell us about the chemical formula. Now, from the chemical formula, we can determine the hydrogen diffusion index, which tells the number of pi bonds or rings in that compound. So an alkane chain will have an HDI of 0 because it has no pi bonds or rings. An alkene chain has 1 carbon-carbon pi bond, so it has an HDI of 1. Note that as the number of H's decrease, the HDI increases, which means there's more pi bonds or rings. Many organic compounds have oxygen, nitrogen, or halogen, so you can calculate the HDI using these rules. So C2H6O has 0 pi bonds or rings. C3H7Cl has 0 pi bonds or rings, and then C2H7N has 0 pi bonds or rings. So based on the HDI, we can speculate on the structure of a compound. For example, C2H6O has these 2 possible structures. It's either an alcohol or an ether. IR spectroscopy tells us about the bond types in a compound. So when a substance is exposed to IR radiation, it causes the bond to vibrate, which means either to stretch or to bend. So let's take a look at an IR correlation table, and let's specifically look at the first 2 columns. So the first column shows the bond types. The second column tells the base value, which is the energy in wave numbers, which is needed to either stretch or bend the bond. So the higher the number, the more energy required to stretch or bend that bond. Note a carbon-oxygen double bond requires more energy to stretch than a carbon-oxygen single bond, and a carbon-carbon double bond requires less energy to stretch than a carbon-carbon triple bond. So you've measured an IR spectrum, then you want to interpret that IR spectrum by matching the peak to a bond type. So stop the video and answer these questions here. So here are the answers. The IR spectrum of ethanol, butane, or acetone is shown below. So stop the video for a minute and interpret the spectrum. So let's take a look at the structure of each compound and the bond types. So note that this spectrum shows a peak at around 3,500. It could be an OH peak, could be ethanol. Here is the CH stretch. this peak here at about 1700 wave numbers is probably a CO double bond. Now, this peak here is probably a CO single bond. So based on all this information, this spectrum is most likely acetone. And this peak is most likely water.